Hi Year 12, this is the first in a series of videos for the topic Geometric Applications of the Derivative. In this video we're going to look at the first derivative. So we're going to cover the sign of the first derivative, stationary points and turning points, the first derivative test, and global and local maxima and minima. So let's start off by revising the sign of the first derivative. Now remember that the derivative is also called the gradient function. It is the gradient of the tangent to the curve at any particular point. So if the first derivative is greater than 0, then the gradient of the tangent will be positive. And you can see that here and here. And the curve is going up at that point. It's increasing. If the derivative is less than 0, the gradient of the tangent would be negative and the curve is decreasing. If it's equal to 0, then the curve is stationary. Gradient of the tangent is 0. There are two types of stationary points. There are turning points, which both of these are because they turn around. There's also horizontal inflections. Also recall that a curve is monotonic increasing if the derivative is always greater than 0. For example, this is an exponential. We can see that the gradient of the tangent would always be positive. So this curve is monotonic increasing. A curve is monotonic decreasing if the derivative is always less than 0, like this example here. So let's look at an example. Find the values of x for which the curve y equals x cubed plus 6x squared take away 15x plus 1 is stationary. So we want the first derivative and we want to put it equal to 0. So our first derivative is 3x squared plus 12x take away 15. And we want y dashed is equal to 0. Now, we can factorize this into two brackets like this, or we can use the quadratic formula. Factorizing is quicker. Using the null factor law, x is equal to -5 or +1. Now, if we want to find the values of x for which this curve is increasing, then we want to solve the first derivative is greater than 0, which in this case is going to involve solving a quadratic inequality. We want this to be greater than 0. So we start by stating the critical values, or the zeros. We just found those, remember. X is equal to -5 and 1, drawing up a number line and marking those two. Now this is a positive parabola, so it's going to come down through here and up through there, so I'm just going to sketch it quickly. We want to know where this parabola is greater than 0, greater than the x-axis, or above it. So that's going to be here and here. So the curve is increasing for x is less than -5 or x is greater than 1. To find where it's decreasing, we solve the first derivative is less than 0. Same diagram, here it's going to be dipping below the x-axis. So the solution is in between these 2 points. So -5 is less than x is less than 1. Here's another example. Sketch the derivative of the curve y equals x plus 1 in brackets 3x take away 1 all squared. So this is just going to involve finding where the curve is increasing, decreasing, and 0. So it's increasing here. We have a turning point, so it's 0 here. It's decreasing here, so it's negative. Another turning point, 0, and then finally increasing. When we go to sketch it, it doesn't have to be super accurate. It's just got to go through here. These are the zeros here and here. It's got to be positive on this side, negative in the middle, and positive here. And just a rough sketch will do. And there we go. Now, one method of testing the nature of a stationary point is the first derivative test. And all we do is test the sign of the derivative on either side of the point. And that'll actually tell us whether it is a maximum, like this one, a minimum, or a horizontal inflection. Let's look at an example. Find the stationary point for the curve y equals e to the x squared and determine its nature. So we need to do the derivative first. Now this is a chain rule. The outer function is an exponential. The inner function is a power rule. So remember, when we do the derivative, e stays the same. So e to the x squared. Multiply by the derivative of the inner function, which is 2x. Tidying it up, we get 2x e to the x squared. And we want to solve that equal to 0. Now, we can use the null factor law here because we've got a product that's going to equal 0. So either 2x is equal to 0 or e to the x squared is equal to 0. But e to the x squared is never equal to 0, so we can ignore that. We just need to solve 2x is equal to 0, which of course gives us x is equal to 0. Now we want to find the stationary point on this curve, so we need the y-coordinate as well. And all we do is substitute the 0 back into the curve. So y is going to equal e to the 0, which is 1. Now, draw up a little grid to do your first derivative test. We want to test on either side of this x-coordinate. So I've got that in the middle. I'm going to test -1 and +1. I'm going to put these numbers into the first derivative. So putting -1 in here, I get -2e to the 1. So -2e, which is negative. Putting the 0 in, we already know we're going to get 0. And putting 1 in, I get 2e, which is positive. All right, let's draw a negative gradient. There's one, a 0 gradient, and a positive gradient, and it is a minimum. Now this is sometimes called the bucket test, just because it looks like a bucket. Now any turning point is either a local maximum or a local minimum. And we can see two turning points here. Here we have a local maximum. That just means it's like a hill, for example. So either side of it is going to be lower. So that's a local max. Here's a local minimum. So it's a bit like a valley. Either side is higher. The global maximum is the highest point on the curve. The global minimum is the lowest point on the curve. Now, if the curve goes off to positive or negative infinity, then this maximum or minimum won't exist. And a local max or min might be the global max or min, or it might not be. So for example, this curve here, we have a local minimum, which is also the global minimum, at the point -2, -5.333, etc. We have a local maximum here at 0, 0, and we have a local minimum at 1, -0.833. The curve goes off to infinity at the top, so there is no global maximum. Here's another example. This curve has a restricted domain between -1 and 4. State the global maximum and minimum. This is a really easy question. It's really about finding the highest and lowest y values. So obviously the global maximum is 1.333 here and here. It's also the same as this local maximum. And the global minimum is going to be -25.333. Okay, that's it for this lesson. In our next lesson, we're going to look at the second derivative.